Today we are going towards subtopic of motor effect of the main section number 6 with the title Magnetism and Electromagnetism over there. Okay, the motor effect can happen when you put a current carrying wire in a magnetic field over there. For example, I am provided with a permanent magnet over there into its north and south pole over there, and I put a coil. This is the north pole and this is the south pole, and magnetic field is going from north pole to south pole over there. When I put a current carrying coil into it, this is the magnetic field in which I want to place a current carrying coil into it, or a current carrying wire over there. Then what will happen? For example, here I am provided with a battery so that current can flow through it. Then a switch is also connected there in the form of a current supply over there. And this is the positive terminal and negative terminal, and current is going in this direction over there. Then what will happen that this wire in a magnetic field, it is really useful stuff like like electric motors. If you want to know exactly what it is, you will have to keep watching this video over there. Okay, current carrying wire is or coil is placed inside a magnetic field over there. Then it experiences a force where I say a current carrying wire in a magnetic field, wire or coil in a magnetic field experiences a force, over there. If we look more in detail, we can say when a current carrying wire is put in between a magnetic poles, the two magnetic fields affect one another. The result is the force of the wire, because we know that when current is passing and according to right-hand grip rule, magnetic field is also produced around this wire in the concentric circles form. And these circles are going to show that the magnetic field is with the help of these permanent poles of north and south pole, and current carrying in the form of uh, their magnetic field with the concentric, they are going to interact with each other, and a force is produced over there. This causes the coil. When the force is present, then the coil or the wire starts to move. Coil or wire starts to move, starts to rotate over there, starts to move in the form of a rotation over there. Then this is called basically a motor effect over there. This is called motor effect, which we are studying as a subtopic over there. This is because the charged particles moving through a magnetic field, when current is passing through them in the form of current is basically related to moving charges which are present in through the wire over there. We can say these moving charges are electrons in the current moving through a magnetic field experience a force, as long as they are not moving in parallel of the fields over there. So this is an aerial view over there that we can take into account. So magnetic field of the magnets are going to be supported with the help of force. And when I take in the case of coil over there, they start rotating over there, or rotations over there, and which is responsible to rotate later on some mechanical work to be done with the help of motor over there. And to experience a full force, the wire to be 90 degree to the magnetic field. The main condition which I will have to tell you here, that the wire which is containing the current over there should be placed at 90 degree to the magnetic field lines, to the magnetic field or magnetic field lines over there. field lines over there. If it is placed at 90 degree, it will experience the force over there. And if the wire runs along the magnetic field, it would not experience any force at all. So at angles between, at angles is in between, if it feels some force, like 0 is 0, parallel case is not feeling any experiencing of force over there. And later on A levels, we will also go for mathematical expression. But right now, just as the point of view that we will have to place that wire which is carrying the current over there should be placed at 90 degree to the magnetic field lines over there. The force always acts in the same direction relative to the magnetic field of the magnetic field and direction of current of the wire. A good way of showing the direction of force to apply a current to a set of rails inside the horseshoe magnet over there. Bar magnet is placed on the rails and complete circuit, and this generates a force that rolls the bar along the rails over there. For example, I say here that, for example, these two are the rails over there which are produced, and on them you are placing a wire over them. This wire which starts to slide over these rails when it is carrying some current into it, and you are providing some permanent magnetic field over there. Like as I say, this whole one is being provided by some magnetic field, like crosses are going to show the direction of magnetic field into the page. If I show with the help of the dots over there, it means the magnetic field is out of page, out of screen, which you are watching right now, out of page and into page. Then it starts to slide over there, which shows that the force is experienced over there. The magnitude of the force increases with the strength of magnetic field. As you increase the strength of magnetic field, then the force is also going to increase over there. And the force also increases the amount of current passing through the conductor. If you increase the current, then the force experienced will also be going to increase over there. So reversing the current or magnetic field also reverses the direction of force over there. If you reverse the direction of current or you reverse the direction of magnetic field, then direction of force will also be reversed over there. And here I will say that for this whole process, when I am relating current, magnetic field, and force, then I will have to move for motor for Fleming's left-hand rule. Fleming's left-hand rule over there, which states that if I observe my left hand over there, then I will say that if the force is in upward direction along the thumb over there, and middle finger is going to show the direction of, I can say, magnetic field, force, magnetic field in the form of V, and current, which is also making an angle of 90 degree here with the magnetic field over there. It is in 3D. So not to worry how to make this angle of 90 degree. I'm saying over there, it is in 3D over there. And then this is for current over there. I'm saying here, when I take my left hand in such a way, Fleming's left hand rule tells us which way your force acts over there. Basically, it tells us in which direction the force is produced or in which way the force acts over there. So I will also tell here that if I am observing that how force it's going to act over there, we will have to take into account. They could test if you do this, so practice it over there using the left hand rule. Point your first finger in the direction of field. For example, I'm taking here, this is the permanent poles over there. This is a north pole, this is a south pole. Put your finger, index finger over there in the direction of magnetic field, like in this form. and place a current carrying wire or coil in the direction of this. And you are saying its direction is upward like that, as I am saying here. And if you are pointing it upward, and then you can say the force will be inside the page over there. And here I say first finger in the direction of magnetic field B, first finger, like index finger over there. And current is going to middle finger or second finger of left hand. And force will be in the direction of thumb over there. This is the Fleming's left hand rule, and everyone is perpendicular over each other. Your thumb will point in the direction of the force or motion over there, and these can be illustrated by the direction if you are taking your thumb and fingers over there in a proper way. On the other hand, if I move towards the this motor effect to be implemented properly in electric motors and loudspeakers over there, then I will say electric motors and loudspeakers over there. Then in that case, I will simply say here that one of the favorite exam topic of all time, this is electric motors related to it. Understand it and learn it properly over there. A simple DC electric motor has a simple electric DC motor. Over there is present, for example. Then I will say here, for example, these are provided by North Pole as a permanent magnet inside the motor. South Pole is also present, and magnetic field is going from north to south over there. And you are providing a coil inside it, which is supplied with the help of split rings commutator over there. Then I am saying, first of all, here, the commutators are present over there. These are attached to the electric battery of the supply over there. And what is happening? The current is entering in this direction over there. And the circuit is getting complete over there. Then in this way, the diagram, if I want to speed up the motor over there, then I have four main factors. It means I can increase the current, like more current should be provided. Then motor will speed up over there. Second way, where I can say more turns of the coil, more number of turns of coil. At number 3, I will say stronger magnetic field. Stronger magnetic field are B over there. And at number 4, a soft iron core in the coil. Use soft iron core in the coil. Then motor will speed up over there. The diagram shows the force acting in upward direction here. Like I'm saying, it is in upward direction and it is in downward direction over there. The force is in the upward and downward direction, acting on two sides, arms of the coil over there. These forces are just useful, which acts on any current in a magnetic field. And because the coil is on a spindle and the forces act one up and one down, it rotates. So force one up, one force up, and second force is down. Then they rotates as like a moment or like a couple of moment of a couple over there. Then they start a rotation in a proper way. The split ring commutator is a clever way of wrapping the contacts every half turn to keep the motor rotating in the same direction. So the function of these split rings is to make motor to rotate in the same direction, not to take the reverse direction over there, because it is a DC motor. And the direction of motor can be reversed either by swapping the polarity of DC supply or swapping the magnetic poles over there. If I swap with the north and south with south and north, I can change the direction of rotation over there. If I change the direction of the negative and positive terminals of the battery, I can reverse the direction of this motor of rotation over there. After that, I will say here that the speed can be increased by adding more turns to the coil, increasing the current, increasing the strength of magnetic field, or by adding the soft iron core. So you can use the Fleming left-hand rule to work out which way the coil turns over there. So this was a complete overview of DC motors over there, how they are producing the mechanical energy in the form of force for the rotation of armature over there. On the other hand, if I move towards my second point here, loudspeaker over there, an electrical signal from an amplifier are fed to the coil of wire in the speaker, which is wrapped around the base of the cone over there, if I observe. And I will say here, for example, this is a speaker shape. What is happening here, basically, this is a cone shape of speaker over there. And it is provided with a coil here at its base. And this is a coil which is getting, and this coil is also having the permanent magnets attached to it in the form of up and down. These are magnets. And an AC signal is given from here to here, as AC signal is given at the base of this cone of the speaker over there. And from an amplifier are fed to the coil of the wire. It is fed to the coil of wire over here. Then I can say this speaker is going to amplify this sound more, and the coil is surrounded by a permanent magnet. So the AC signal causes a force on the coil and make it to move back and forth. So this coil is moving back and forth to the coil, just like an elastic spring over there. So we can say these movements makes the cone to vibrate, and this creates the larger sound over there. At the base of the cone of a speaker over there. After that, I will have to move towards electromagnetic induction, and also towards, I can say, I will have to move towards transformer section. So let's move now towards transformer section and more detailed section of electromagnetic induction over there. Electromagnetic induction. This is very important and conceptual topic over there. If I want to go more in detail of this topic, I will simply say here, first I am taking a coil which is present over here in the form of a coil. I'm saying I'm placing it, and I am connecting it with a galvanometer, which is showing that there is no current. When I am taking a magnet bar over here, which I'm not inserting right now, but I'm just saying that it is a south pole and north pole. When I take it in, like I am moving in first cases, move, first case I say at rest outside, then I will say EMF induced is equal to 0. When moving in of magnet, what will happen? That I will observe that there is a change in this deflection over there, which means EMF induced. EMF induced over there. And the third case, I'm saying here that the magnet is present inside the coil, but at rest. At rest inside the coil, like magnet has reached inside the coil, magnet inside the coil at rest, then again my EMF will be shown by galvanometer in the form of zero deflection or production over there. On the other end, when I am moving out, then what will happen? It will change its deflection direction. Means at number 4, when moving out to magnet bar, then EMF will be induced in opposite direction. So these were the 4 cases which we will have to study over there. Now he is saying to induce the current in the coil of the wire, there must be a change in interaction of magnetic field lines with the coil of the wire. So remember that when I am entering this magnet bar, it is going to interact and magnetic field lines through this wire of the coil over there is going to change. Then we can say this change in magnetic fields is a compulsory unit. Change in magnetic field lines. Magnetic field lines interaction with the coil must happen. Then the current will be induced and can be detected on the galvanometer over there. Galvanometer over there in the form of deflection, and you can detect that the current is induced into the coil over there. At the number 5 case, if you are entering a stronger magnet, more EMF will be introduced. If I am saying here in number 5 case, if magnet entered, magnet of magnetic field strength of stronger over there, then I will say more EMF will be induced. Over there. And at number 6 case, if there are, I am saying here, if I increase the number of turns of the coil, then more number of turns of the coil will also be responsible for more EMF will be induced over there. At number 7, I will say here that moving the magnet at faster rate, moving in and out of magnet at faster rate is responsible for more EMF induced over there. These are the 7 cases till now, which I have told you. So always remember that here, as I said, magnetic field lines interaction should change to induce the current over there. Then behind this whole phenomenon, there is a law that is called Faraday's law of electromagnetic induction is available. Faraday's law of electromagnetic induction states that EMF induced in a coil is directly proportional to rate of change of magnetic flux inside the coil is directly proportional to each other. So EMF induced in a conductor is directly proportional to rate of change of the delta phi is magnetic flux linkage. Magnetic flux linkage is basically going to explain the Faraday's law of electromagnetic induction over there. So we can also say the faster the rate of change of interaction, the greater will be the EMF induced according to this law over there. And the other law, which is also in opposition, is going to work. That is called Lenz's law over there. This law is called basically like EMF, which is induced, like EMF induced is always such that is always such that to oppose such that that it opposes the change which produces it. Which produces it over there. So till here, Lenz's law is being cleared now. So the current in the coil is always such that it its magnetic field try to oppose the motion of the magnet. So remember that the current which you have produced and detected with the help of galvanometer will always there to induce another magnetic field which will oppose the motion of magnet in and out in both cases over there. I will say here that there is now we should move towards AC generator over there. That I will have to move towards AC generator now. That is also a part of electromagnetic induction over there. So AC generator. AC generator, basically, I can say here, it is used to convert mechanical energy to electrical energy over there. Electrical energy over there. And such device, like turbines, rotates and converts the rotational mechanical energy into the electrical energy can be taken into account. For example, I am saying here there are the permanent magnets in the form of north and in the form of south pole. And you are taking a coil of many number of turns, like one coil, like two coils, like three coils, and all three coils are available and going to interact with directly attached to slip rings over there. Like for example, I'm saying here it is a slip ring. They are going to attach with it. And this slip ring is provided with carbon brushes to reduce the friction of AC generator over there. These carbon brushes are attached to a bulb over there, which is going to show that it is getting to light up when current is going to flow through it over there. So slip rings are available, permanent magnets are available, and carbon brushes are available. So these are the parts of basically component. So if I talk about AC generator, then its working principle is Faraday's law of electromagnetic induction. Electromagnetic induction is present over there. And I am rotating this coil with the help of some mechanical energy. And the rotation is going to be observed by the north and south pole of permanent magnets, and current is induced and bulb is lighting up. If I talk about components of this circuit of this AC generator over there, then I will say here that these components are basically permanent magnets. And I will say that it provides a strong magnetic field with which the coil interacts to produce EMF. At the number 2, that is a coil about which I can say it rotates between the poles, cutting the field lines, and EMF is induced in it. After that, I'm saying there are slip rings. Slip rings are basically, they flip the direction of the current in the external circuit when the coil crosses the vertical position over there. And in the last, there is carbon brushes over there. And these carbon brushes are there to reduce the friction and provides a contact between a ring and external circuit over there, slip ring and external circuit over there. And I will say here, when coil winding is rotated with the fixed axis, this cuts the field lines of the permanent magnet, and the cutting of the field lines by the coil causes the rate of change of magnetic flux linkage, and EMF is generated in the coil, and which is responsible by Faraday's law of electromagnetic induction over there. Sometimes it is asked describe how a current is induced in a coil. For 4 marks or like that, or increase the magnitude of the current. Then the reasons like that: increase the strength of magnetic field using strong magnets like that, increase the number of turns, increase the speed of rotation, increase the wind the coil on a soft iron core over there. So the remaining all key factors to increase induced EMF, we will have to go over the same criteria of electromagnetic induction. We can increase the strength of magnetic field. We can increase the amount of current in the coil. One can increase the number of turns of the coil. We can increase the speed of magnet to move in and out like that. That is being here. It will be taken that the coil should be rotated at faster rate over there. So overall magnetism can be controlled by these factors over there. If you double the frequency, EMF will be doubled and half time will be half over there. And the last topic which I will have to take is transformer. Transformer is a device which is used for step up or step down by using a transformer in the number of turns of primary coil and number of turns in secondary coil, and voltage into the secondary and the voltage into the primary and current in the primary and current in the secondary. These are some variables which we will use for step up and step or step down of a transformer over there. Let's suppose there is an iron core, and along this iron core, at the one end where the input is given, I say that is a primary end, and number of turns in the primary coil is shown like this, and number of turns in the secondary coil are shown like this. These are the number of turns in the primary, these are the number of turns in the secondary, and I am providing an input voltage, yani V in here, and on the other end I am getting V out over there. Then according to his number ratio of turns of the coils over there, what will happen if NP, number of turns in primary, is smaller than NS, then it is, as number of turns in secondary is high, so I say it is step up transformer, in which we can say mostly when we look towards the generation house or hydroelectric power plant and far away to the 500 kilometers away the electricity is supplied, then we will have to use step up transformer over there. Because during, if the voltage is not high, then the current will become high. And if current will become high, there will be too much energy losses over there. So we will have to use step up transformer. On the other end, if I am using the same transformer with the larger number of turns in the primary and very low number of turns in the secondary, then it means NP is much, much greater than NS. Then you know it is step down transformer, which we will mostly use in our mobile phone charger. We observe that 220 volt is given and it is being given as 10 volt over there. So this is the way how to go with the proper way of working. So NP and NS both are being taken as a step up transformer and step down transformer for both of these cases over there. After that, when we are done with the step up and step down of the transformer, I will say here that always keep in mind the formulas of step up and step down over there. Always keep into mind that is, if I am taking NP over NS, then VP over VS is going on. It's good. On the other end, if I take for current NP over NS, then I will have to take the reciprocal IS over IP over there. For current, the turn ratio is like this, and for voltages, the turn ratio is like this over there. And I also tell you, always remember that the power across the primary coil will always equal to power across the secondary coil. So P is equal to VI. VP IP will equal to VS IS over there. So by using this relation, you can also take VP over VS and IS over IP over both of these cases over there. Remember that for the transmission lines, for transmitting the electricity from its source, we will have to use the step up transformer. For other applications, we also use for step down transformer over there. So this was the way how to go with the electromagnetic induction chapter over there. In the next one, we will move towards the section 7, that will be radioactivity and particles. 2 more sections are pending, so stay connected with the videos and lectures over there. Thank you so much for today. Allah Hafiz.